Good afternoon, my name is Daniel Perez, and in this lab we examined how the hanging mass affects acceleration while using percentage error and percent difference to analyze the results. So this experiment is based off of Newton's second law of motion, just like the other one was, which basically states force equals mass multiplied by acceleration. In simple terms, what that means is how fast something speeds up depends on how strong the push or pull it is and how heavy the object is. We calculated theoretical acceleration using the formula provided, which was hanging mass times gravitational acceleration over hanging mass plus the glide mass. We only increased the hanging mass while keeping the glide mass constant. Increasing the hanging mass increases the pulling force, so the acceleration was expected to increase. Before we collected the data, we calculated the new theoretical acceleration and compared it to the original theoretical acceleration using percentage difference to predict how much the acceleration would change. After we ran the experiment, we calculated the new experimental acceleration and compared it to the theoretical value, and we did percentage error on that. We also compared the old and new acceleration using percentage difference to evaluate how much the acceleration changed. So basically how this would relate to the real world is when you add mass, it changes how an object moves. For example, a car carrying more people will not speed up as quickly as the same car when it's empty. So people that engineer buses, for example, this is very useful to them. Or something as simple as planes, you calculate how much it would change. It would change fuel costs, for example, having more mass on your plane as opposed to having less mass, which would be the passenger's cargo. And that's it for me. Thank you. So for this lab, this is what we're using. We're using the capstone program. This is our graph. We are using our laptops. We made here some data.
Also using a calculator.
Doing calculations. We are using this
Motion detector.
The glide. We also have the new 20-gram weight compared to our old 14-gram weight from our previous experiment. We also have the glide and this.
You said in the middle, but that's as far as the string goes. So.
Yeah. Where's the weight?
Here you go.
Thank you. Okay, so basically what we're going to do is we're going to have that machine on. So you can turn it on. We're just going to release it and get the graph from it. So that's all.
Alright, tell me when. Yeah.
Plug it.
Yeah. That was. Quick pause. Yeah.
Right. Just testing to see if it runs properly.
It's like hardly moving.
I'm pulling it all the way back.
Leave it on?
It's accelerating. So we'll try like as far as it can go.
It's not capturing it.
You're putting it a little down. No.
Press it. Go ahead. Just to make sure.
Alright, you want me to delete this?
Yeah, please. Let me just read through these.
After fixing and placing,
Yeah.
right? We're going for test one.
Go to the first little. Yeah. So
Better not say something like reference field or something.
we're gonna have to do the rise over run stuff.
So like between the peak, the lowest point and the peak?
Hold on, because I don't remember. Do you remember?
I remember some of the thing was that we had to take 2 points right here and then 2 points right here. And
I can pull up the last lab.
yes.
Yeah, you probably should.
Do you know it?
Oh, I believe it
It's a
was.
little thing next to this. It's right here.
This one?
Yeah.
Yeah.
Or do I like randomly hand it?
Do you remember how to?
Yeah.
Square. 2.5.
2.5 what? Velocity?
Yeah. We got 0.7 last time.
And plus our theoretical is 0.68. So it sounds like that's right.
Yeah.
I don't think it's... You just want to ask?
You can if you want to.
Oh, that's our acceleration?
From what I remember, yeah.
Placing the right graph. We
Maybe.
got this.
I wasn't here last time.
We can do it by hand too. Have you got? Let's select the points.
Yeah, if we get the same answer with the points, then yeah, it's right. No, you just right click on the points. Or not right click, just click on it.
Just click them.
Yeah. Then
Oh, I
the
see.
first one? Yeah.
To
And there's that lowest one.
the lowest one.
I think so, because that's when it bounces up. I think.
Yeah. All right.
Like that point and then it starts to go back up, so that means it bounces up. Not the lowest one. I would say the lowest one. What about you guys?
Lowest.
Okay. So
Then X.
T1, okay, so for position 1,
T1 minus.
it'd be the negative point. So it'd be at 6 seconds.
T2 is.
1.55. This was 6 minus the experimental, which was 0.56.
Yeah.
And then the bottom is 0.56 again. Because
Oh, it's negative 1.
which one?
The experimental?
The new one that we got?
Yeah, negative.
Fucking pen's giving out.
Hello, my name is Angel Ortiz and I'll be going over our data and conclusion for Labs 4, which includes lab data for Lab 3 as well. So for Lab 3, our acceleration was negative 0.70 meters per second, our hanging mass was 14 grams, and our glide mass was 180 grams. While for Lab 4, our acceleration was negative 0.686, our hanging mass was 20 grams, and our glide mass was 180 grams, so that stayed the same. Now, if we compare our theoretical acceleration from Lab 3 to Lab 4, we see that it is a 2.04% difference, meaning they're pretty similar to each other, but Labs 4 theoretical acceleration is faster than Lab 3. Now for labs 4 experimental acceleration, we got negative 0.56, right? And if we compare it to our theoretical acceleration, which was negative 0.686, that is an 18% error difference. Meaning it's a pretty big difference between what we thought it was going to be and what it actually was. Now, if we compare our experimental acceleration from lab 3 to lab 4, we'll see that it's a 20% difference. It's 20% difference in the two, which makes sense because we are using a bigger weight, meaning it should have some difference in between speed. Now, the 2 error percent difference between labs 3 and 4 should be similar because you want a low error percent, because the lower your percent error is, that means the more accurate your calculations was in finding out the acceleration. Our percent errors are not similar. Our percent error for lab 3 was a lot lower than our percent error for lab 4, meaning our calculations for lab 3 was a lot more accurate than for lab 4. Now, the percent error should be small, because the smaller it is, that means the more accurate your calculations were. So if you get, in between 10%, that means there wasn't really that big difference. But then, anything higher than that, it means there could have been meaning there was a big difference. Now, in order to get a better percent error difference, we would need to rerun the experiments until we get that smaller percent error difference. Now, our lab 3 experiment did have high accuracy due to the lower percent error difference. And what I think could be affecting lab 3 from lab 4 is just user error. I think in lab 3 we were probably just a lot better at doing it than lab 4.